everybody. Welcome to the session on cross-domain recommendations. My name is Marko Tkalčić. I'm from the University of Primorska in Slovenia, and I'm happy to introduce our first speaker. This is Shao Xing, who will present the paper DREAM and Supervised Contrastive Learning for Cross-Domain Sequential Recommendation. The floor is yours. It's over there.
Hello, everyone. Hello, everyone. Thank you for joining, especially thanks for you guys joining to see how we make the dream come true. Today, we are presenting the topic is about using dream and supervised constructive learning to provide the cross-domain sequential recommendations. My name is Xiaoxing Ye, and also you can call me Sean. I'm coming from University of New South Wales University, coming in Australia. And my colleague Lin Yunli, Lina Yao, is my supervisor in the Cyril District 61, Australia. Today's presentation will be including 3 parts. The first part is about the task, motivation of the cross-domain sequential recommendations. And then we will go into the details about how the dreams work, starting from the architecture. And then we explain how we apply supervised constructive learning and how we apply the constructive learning and Vauxhall laws to cross-domain recommendations. Lastly, we will go into the experiments and the results. Cross-domain sequential recommendations is mainly leveraging the cross-domain information to provide more accurate recommendation for the customer. Normally, we have a rich domain and we have a sparse domain. Normally, the recommendation can have performed very well in the rich domain, but it normally performs poor in the sparse domain. That's why we can think of leveraging the cross-domain information to mutually enhance the cross-domain recommendations. Here is one of the examples. When we have the book sequence, and we can leverage that to predict the book recommendation. When we have the movie domain recommendations, we can also use the movie sequence to predict items. But whether we can combine these 2 sequences together to predict what might be the last item the customer is more likely to purchase or will. Apart from these tasks, we also identify 3 main key relationships, starting from the interest sequence, saying that we want to leverage the information, intrinsic information within the sequence, like the customer purchased the romantic book and then purchased romantic book again. The second relationship is about the cross-domain relationship. The customer might look at the comedy book and then look at the comedy movie again. The last one is about the inter-sequence relationship. It's saying that if the 2 customers share the same interests or share the same target variable, ideally, they should be sitting close together. If they do not share the same interests, ideally, they should be slightly separate apart, so that the performance will be even better. And then we will go into the motivation and the contribution of the tasks. Starting from the first contribution is about introducing the dream architecture. You may wonder, what is the dream? Dream is representing for the decoupled representation and extraction attention module. The module is made to allow us to learn the single domain representation as well as cross-domain recommendations, and also allow the cross-domain recommendations to learn the information from the single domains without sacrificing the performance in the single domain. And then we have the supervised constructive learning. The key motivation is trying to maximize the relevancy between the single domain and cross-domain. Also, we want to maximize the relevancy between the inter-sequence who share the same interests. We also want to minimize the relevancies between the intra-sequence with different interests. Lastly, we introduce the Vauxhall laws to address the class imbalance problems. Dream architecture including 5 main steps, starting from the sequence. We generate 3 main sequences, starting from the X domain sequence, Y domain sequence, and cross domain sequence. After that, we have 3 separate transformers to learn the intrinsic information within the sequence. And then we can generate the representation for the domain X, domain Y, and cross domain. You may be wondering, this may be already enough to predict the model. Yes, it's okay. But we also want to use the extraction and attention module to further enhance the cross-domain representation. But I think definitely less slides we go into even more detail. But one thing I want to call out here is about the stop gradient operation. Based on our experiment, we find that cross-domain recommendation is very hard to learn the cross-domain representation. That's why we want to use the extraction and attention module to learn from the single domains to extract the information from single domain to refine the cross-domain representation. And the stop gradient operation is to avoid the opportunity the lossy pattern from cross-domain pass through the single domain. But definitely you may wonder whether it actually have impact. And then in the aberration study, we will tell whether it actually have a mass impact there. Now we go into the details about the scheme architecture. Firstly, we have the transformer. We use the unidirectional to ensure the causality. And then we have the domain extraction layer. It's a very simple neural network, but we have the stop gradient operation there to avoid the lossy coming back to a single domain. Lastly, we have the gating, which also is about attention module to allow the cross-domain representation to select the information from single domain. And then we also have the supervised constructive learning here. You may be wondering why we use supervised but not original unsupervised version. In original setting, constructive learning, every customer will be labeled as a mutually negative. But if the customer, they share the same interests, whether we can label that as a positive. Because you can see, if the customer share the same interests like the user 1 and 3, ideally they should be sit close together while they set fast apart. In this case, user 1 and 3 will be a false negative if we in original setting. That's why we want to change into a supervised constructive learning. And then here is how it actually works. For each user, we have the single domain representation, cross domain representation, also we have the argument representation. For all the users, all the representation will be mutually positive within the same user. If the user 1 and 3 share the same interests or share the same target, they are mutually positive as well. But when coming to user 2, because they do not share the same interests with user 1 and 3, that's why user 2 will be a negative sample for user 1 and 2. And then the last one is about a formula about how we calculate the constructive loss. And then we go into the Fourier loss. I guess some of you might already know what is the Fourier loss, but I think just want to recap. Fourier loss is a weighted function of the cost entropy. And on the right-hand side, it's more visualized, easier. The main motivation of Fourier loss is trying to downrate the product recommendations, the product prediction with a lower probability. If the product is well classified, we want to downgrade or downrate the learning rate. Here on the y-axis is about the gradient ratio. When the gradient ratio is larger than 1, that means the Fourier loss will be learning faster. When the ratio is less than 1, that means the Fourier loss will learn slower. You can easily tell when the probability of the ground truth label is larger than 0.5. The Fourier loss have a much lower gradient than cost entropy. When the probability of the ground truth is less than 0.4, the gradients of the Fourier loss will be faster. So it will allow the model to learn faster when they have a poor performance. And then after we understand the whole architecture, we will explain about how the experiment settings. In our experiment, we select 2 scenarios in AWS datasets, coming from the food and kitchen, and also have the movie and book situation. Lastly, we also select about 4 categories of algorithm to compare the performance of the algorithm. Starting from the cross-domain collaborative filtering, also have the single-domain sequential recommendations, also have the constructive learning and cross-domain sequential recommendations. And then we come into the experience results. We find that our algorithm has much uplift than the state-of-the-art algorithm. We have around 70% of uplift in quite a few metrics. And one key interesting thing is that all the sequential recommendation is much better than the cross-domain collaborative filtering. And the constructive learning algorithm is performing similar with the cross-domain sequential recommendations. This is the second data set that we have tested out. We found in this data set, our performance also outperforms along and every algorithm, but the uplift will be slightly smaller. And then here we have the aberration study to demonstrate each part of the algorithm, how it actually contributes the uplift. Firstly, we use the SS4REC as a benchmark to tell whether actually the cross-domain sequence is actually harder to learn or have a lot of lossy patterns. When we only use the SAS rollback to train the cross-domain sequence, and also use only cross-domain sequence to do inference, the performance is much smaller than the single domain sequence to learn two transformer and inference in two single domains. And then when coming to the GEM architecture, our algorithm is performing better than the original algorithm. And also, one key call out here is about the stop gradient. You can compare the -SG, which is the remove gradient operation, with the GEM architecture. If we do not have the stop gradients, the GEM architecture will downgrade the performance around 10%. If we include stop gradients, we can uplift the performance from 5.95 to 6.31. After that, we also want to call out the performance about constructive learning. You can compare the past FL and past UCL, which is the unsupervised constructive learning. It upgrades the performance from the 6.67 to 8.04. Lastly, when we compare our algorithm with the unsupervised constructive learning, the final performance has another 10% uplift. Lastly, we also have one case study to demonstrate whether the algorithm can maximize the similarity between single domain and cross domains. We can tell from here, when we compare with GEM architecture, it's about 0.58. And after we adding the constructive learning, and then we can able to bring the similarity from 0.58 to 7.7. Thank you very much. I think this is the main context for the presentation. Thank you very much for coming, and especially thank you very much for seeing how we make the dreams come true. I think it's time for answering the questions.
Thank you, Xiaoxin. Questions, please. So if anybody has questions, please go to the mic. Okay, I have one question. So in your toy example at the very beginning, you shown how you have like romantic movies and romantic books, and this was like the underlying, let's say, rationale why you went into this. How would you extend your work in such a way that you could also explain cross-domain relationships? I mean, something is between movies and books, and this is relatively straightforward as your toy example, but how would you explain things where relationships when it's less obvious?
To be honest, I haven't think about that in very details, but I think I can try to think about it in a real-time manner. I would say, firstly, potentially we try to see whether we can leverage side information, for example, whether they coming from comedic or the romantic or any scientific movie. If we use the category of the book or the movie, potentially can help us to explain it a little bit more to see whether this information actually can be crossed over to other domains.
Okay, thank you. I have another question actually. When you shown some improvements in your results in NDCGs and so on, did you perform any statistical testing to show whether the improvements were significant or not?
Yes, we have do a statistical test for quite a lot of the tests, and then you can easily tell here within this aberration study, all the steps will be statistical significance except for one I remember. I think here it will be more easier to tell. When we add the Fortier loss, there is not a statistical significance except for adding the Fortier loss, the gap will be statistical significance.
Okay, thanks a lot. Any question? Okay, then let's thank our speaker. Thanks, Xiaoxin. And I invite the next one, Zitao from Shenzhen University.